Hey everybody, it's Ripley back again. Today we're going to talk about triple integrals, which are nuts. So if you recall, before when we had double integrals, we had a domain that lived in the xy plane, and then we sent that up to a z value. So we're like a z equaled f of xy, right? Remember that? And we found that we could find volumes of solids if we basically found the volume underneath the curve, et cetera, et cetera. We've done these for days. Well, triple integral is a little bit different, and it's a little crazier. Here's why. It's really hard for us to wrap our brains around what a triple integral means geometrically, because what we do is we write the triple integral like this, with this e. Remember before, this was our d, all right? And then now instead of having f of xy, we have an f of x, y, and z, right? And then we take this dv. Now what is this v? What I've created here, I drew this in advance just because I didn't want to make you guys suffer through me doing it. What we have is we have this volume of this box or this enclosure. That's why it's got the E. I would prefer a B because it's more natural. All right. And we take little itty bits of this thing and we send them off to some F somewhere else. F does not live in this plane. All right, or excuse me, in this space, in this 3 space. F lives somewhere else. So geometrically speaking, it spits itself into a true 4th dimension. Now, we can't wrap our brains around that. That's very difficult to understand. But understand that we can still take triple integrals, and we'll get into some applications of triple integrals in this section later on down the road. All right, excuse me. But I want you to sort of try to wrap your brain around what's happening. As long as there is an F sitting in there, then we are sending values of x, y, and z. Those are the domain, and they get sent somewhere else. Now let's talk for just a minute what this dv right here is. What is that? Where does that come from? Well, it's a change in volume. And by virtue of the fact that it's a change in volume, you can probably tell that this little cube, just like our little rectangles when we were integrating in 2 space, or our little prisms when we were integrating in 3 space, now we're grabbing a cube which has this width right here would be delta y, right, because it's parallel to the y-axis. This would be delta x, delta x, and this guy would be delta z, all right? And when I take an infinite number of infinitely small ones of these guys, well, predictably, shoo, look at that. Ooh, I get to connect the arrow. That's awesome. All right, so that's what that dv is. However, that's going to get a little crazy in terms of the way that we order this, because your spidey sense is already probably tingling a bit, because you can probably be like, well, Ripley, we could do dx dy dz, or we could do dx dz dy, etc., right? I mean, I can do dy dx dz all the way through all 6 possibilities, right? 3 factorial, right? That's the number that we could do. Well, what we're going to do is I'm going to give you an example, and it's actually going to link directly to one of the applications of triple integrals, okay? So I'll give you an example, and we'll play with this, and we'll see how this plays out in the next little section. I'm going to try not to spend a ton of time lecturing at you guys, because dealing with triple integrals, best policy is just to do them, okay? But I need to give you some guidance, because this gets pretty crazy pretty quickly. All right, I'll see you in the next little segment. Okay, before we get into the nitty-gritty of this, we need to start talking about types of regions, okay? And you guys know how horrific an artist I am, so you'll excuse me if I steal from a colleague's work a little bit. Come on, get out of there. Oh, I should be on here before I escape. All right, now check this out. This is pretty fun. All right, now look close. Notice that you have exactly the same thing that I just wrote. This guy is intrepid enough to say, oh, I can say it's a boxed region, right? So what he's saying here are just little boxes instead of these enclosed regions. But don't worry about it. It's all notation. All right, what we have is we're going to have 3 types of regions. And within each one of these regions, we're going to have 2 more types we're going to have 2 more ways to set up our integrals, and that can get a little confusing. I'm not going to go into it in this video. We will talk about it, okay? Just a little bit in an example that I do, and then we'll talk about it in class. So here's how a type 1 region works. It's really simple. The domain lives in the xy plane, all right? And then we have this solid that is created between 2 z values. I've got this z equals u sub 2 of xy, right? So that would be the top side of it, and u sub 1 of xy, which is the bottom side of it. So we're creating a three-dimensional space by locking it between two z values. But we end up, let's be clear, that this thing is not necessarily sitting right down here in the xy plane. It's floating in space. Now, this chunk is this f of x, y, z, or excuse me, is this e right here. This f of x, y, z can be anything. It can be anything. But what's important is that we are defining the values that go in to this function by virtue of this region right here, this e region. Okay, this is a type 1 region. A type 2 region, the domain lives in the yz plane, and the actual enclosure lives, notice, out the xy. Now it's wedged between x equals u1 of yz and x equals u2 of yz. So we have this thing bounded above and below by u2 and u1, and x, those things are functions of y and z. Now, the reason that they introduced this u1 and this u2 is, well, I guess it's so that we realize that we have this boundary going on. If somebody can come up with a better way of describing that, I mean, I don't really understand why they do that specifically, but when we start setting up these integrals, I think you'll understand a little more clearly. Last but not least, we have a type 3 region. Now, predictably, our domain lives in the xz plane, and now we have this enclosure, this enclosed region, bounded between two values of y, u1 at xz, and u2 of xe, and that creates this e. That's going to create our limits of integration. Now, I can't say this vehemently enough. This f of x, y, z can be anything. It has zero to do with this at all until we get rid of it. And when we get rid of it, predictably, and I'll comment on this a little bit, when this goes away, if this is just a 1 and we're left with just a dv, can you figure out what that integral would give us? So if I click back over here, can you tell me what the integral of this is? What would it be for any of these three types of regions? Well, predictably, hopefully at this point you kind of understand how integrals work, particularly in 3 space. You get the volume. You get the volume of E, which is really important and super useful. All right? And we're going to use that a ton. In fact, I'm going to do an example with you here in just a second. Now, before we get too far ahead of ourselves here, what I would like to do is I just want to do an example, a real simple example with you. I want to take the integral from 0 to 1, the integral from 2 to 3, and the integral from, I don't know, 1 to 4. All right, I don't know if I can draw that, but we'll see, of x squared yz. And I'm going to do it this way. I'm going to say this is going to be dz, dy, and dx. Now remember, we work from the inside out, so these limits are on z. The integral from 1 to 4 deals with z. So the only thing I worry about is that guy, right? The limits from 2 to 3 are for y, right? And the limits from 0 to 1 are on x, right? And also remember that Fubini is completely in effect. So if I want to reorganize these, I can do all kinds of things. And because this thing is a product, remember what we're allowed to do. If I want, I can do what, well, you tell me, what can I do? I can either work from the inside out, so this would be the integral from 0 to 1, the integral from 2 to 3 of x squared y z squared over 2 from 1 to 4 dy dz, right? That's easy enough, right? And then this guy turns into what? That's just going to be a constant that I can throw out. So 16, what's that? 8 minus a half is 7.5 or 15 halves. I want to make sure I don't do that. I don't screw that up, right? That's going to be a constant. So I could take out 15 halves times the integral from 0 to 1, the integral from 2 to 3 of x squared y dy dx. Whoops, I did dz, didn't I? I'm a fool. Let's get rid of that. Hopefully you guys caught that before I confused you too much. Bam, there, that's an x, right? And then I deal with the y. So this becomes 15 halves times the integral from 0 to 1 of x squared y squared halves from 2 to 3. Oh man, I did not pick good ones, did I? dx And this, what's that going to be? 9 halves minus 4 halves, that's 5 halves, right? 9 halves minus 4, 5 halves. Pull that guy out, and what do I end up with? 75 fourths. So 75 fourths, it's constant, I can pull it out, times the integral from 0 to 1 of x squared dx. And this turns into 75 fourths x cubed thirds, that's times of course, from 0 to 1. So that turns into 75 twelfths. Now you may have already realized, Ripley, it's a product. I can pull the whole thing apart if I want to, right? Remember that rule? If everything's being multiplied together, then I can take the integrals separately and just multiply them. And that's sort of one of the consequences of Fubini's as well, which is really nice. But what we're really doing, what I want to show you here is, first and foremost, what's happening? Do I want to kick over to another page? I don't think I need to. What this basically does is it takes the enclosure, that E. So here's X, here's Y, and here's Z. All right, and I went, what did I do? I went from 1, 2, 3, 4. I went there, and then Y, I went from 2 to 3. Oh, I'm really going to screw this thing up, aren't I, when I try and draw this? And X, I went from 0 to 1. Oof. So what I'm going to end up with is, oh God, help me. I'm going to end up with, oh gracious sakes alive. Oh, this is going to be awful. Lord help me. I'm going to end up with this solid. Ooh, that's not bad, guys. That's not bad. This right here is my E, right? I put my limits on X. X was the last one to be dealt with. This is from 0 to 1. My limits on Y were from 2 to 3, right? This is from, I can't get in there, 2 to 3. And then my limits on Z, ooh, that's obnoxious, is from 1 to 4. And what it did is it built this enclosure right here. Now, you may say, Ripley, what, huh? I thought this had something to do with this. No. Remember, this enclosure, right, which in this case is this stupid little rectangular box is what it is, got sent into this function somewhere else in another dimension. And that's why we have a difficult time geometrically wrapping our brain around how these things work. Okay? Now, what I'm going to do is I'm going to prove my little, well, I'm not going to prove my little statement earlier, but I'm going to give you a really cool example of how to deal with, well, let's put it this way, triple integrals where they're not as pretty as this, okay? So I'll meet you on the next page. I'm going to draw something for you so you don't have to sit there and suffer through me trying to do this again, all right? I'll see you in a second. Okay, you guys, we got a little cooking show mathematics going on right here. So before I get into this, I wanna back up something that I said because I don't want to be trite about this, okay? What I said that was that the volume of the enclosure, if it were written in this way, if I had a triple integral over that enclosure with a 1 here, right, with 1 dv, that these two things are equal. And that's a bold statement. And the reason that I want to back that up is because it's kind of difficult to wrap your brain around that. So let's say that we had a simple type 1 region. All right, that would imply that I had a double integral, and then I'd have this integral from u1 of xy, these are the limits on z, right, up to u2 of xy. And then what I would have is I would have a dz and then a dA. Now, I am not claiming that dA comes from limits on x and y, right? So what would this turn into? Well, this would turn into the integral over D, right? This D would be the region, the domain region. And then the antiderivative of 1 dz is just z, right? And that would turn into, let me write that up. This would turn into z from u1 xy up to u2. Whoa, something just clicked on me. Hold up a minute. Oh, man. Oh, gracious sakes, I don't know what just happened, but we're just going to keep rolling with the punches. u2 of xy, dear God. All right, and this would be dA, right? This would turn into the double integral over a domain. I'm not claiming that the outside integral is x or y. I'm simply saying it's over some domain. And this is u2 of x, y minus u1 of x, y dA. And we showed earlier, I think it was 15.3, I don't remember which section, that this is actually equal to the volume of a solid, which we are now calling that solid an enclosure. This is just the volume of E. Okay? I want to make sure that I address that before we get too crazy with this, before we get ahead of ourselves. So what I would like to do is I would like to figure out the volume of this tetrahedron, all right, that is bounded by the plane x plus y plus z equals 1. That's an easy one, no brainer. I've got it drawn rather, I don't know, poorly. It took me a little while to do, to be honest with you. Let's see the xy, the yz, and the xz planes. All right, so you can kind of see it. It's just a tetrahedron. It's like a four-sided die, right? You with me? All right, so I want to show you how this works, and I want to show you why I'm going to do it I'm going to set up all 6 integrals, okay? So here goes. D1 is what happens when we're talking about, I don't want to get too crazy, but hopefully you can see the xy plane, this triangle, right? And the line that goes like that. All right, so the way that we can write D1 is the set of xy such that, now I can either go x lives between 0 and 1. So I'm going to have x be the constant. Remember, if I'm going to end up with a number at the end of a triple integral, the outside integral sign has to have numbers on it. So keep that in mind for just a minute, okay? And the set of y that lives between. Now, what does y live between? Y does live between 0 and 1, but y has to be a function of x, doesn't it? It's got to be, because we use numbers for x. Now I have to use a function for y. So y lives between 0 and 1 minus x, because that's the equation of that line. Similarly, I'm going to try and close the bracket, but yeah, that's the best I can do. Similarly, I can say it's also the set of xy such that y lives between 0 and 1. Now I'm establishing that the outside integral will have limits from 0 to 1. And it might be more instructive if these had different numbers, but I think you can follow along. And x lives between 0 and 1 minus y. Okay? So that's D1. Now, without loss of generality, hopefully we can all see that we're going to end up with the same sort of situation. However, let's be careful. This is going to be D2 equals the set of yz now, right? You see why? Yz such that, now I'm going to let y live between 0 and 1. And I'm going to let z live between 0 and 1 minus y, right? So z lives between 0 and 1 minus y. And then I'm also going to set this up as, the set of yz such that z lives between 0 and 1 and 1. And what does y live between? Well, y lives between 0 and 1 minus z, because that's the equation of the line. Right? Excuse me. Hopefully that makes sense to you. Likewise, last but not least, D3 is going to equal the set of xz such that, let's go with x's again, right? X lives between 0 and 1, and z lives between 0 and 1 minus x. And last but not least, I'm not even going to close the brackets, you lazy jerk, xz such that z lives between 0 and 1 and x lives between 0 and 1 minus z. Okay, now what we're going to do is we are now going to clarify what E is. And there are going to be 6 ways to do this. And this gets a little bit tricky. Okay? Because you got to remember, what we're going to have is we're going to have limits. In this case, we're going to have limits. When I'm dealing with D1, I'm going to get 2 sets of different integrals. So we'll deal with this first set, this guy right here first. It's going to be the set of x, y, and z such that we end up with x between 0 and 1, y between 0 and 1 minus x. Now, what does z live between? Well, just like y went from 0 and then it used this boundary line, which we call 1 minus x, as our top bound of y, what is z bounded by above? Well, that should be relatively obvious. Z equals 1 minus x minus y, isn't it? And z starts at 0 because it starts at the xy plane and it goes up. So z is going to live between 0 and 1 minus x minus y. Now, I don't like the way the book does this. I don't like the way the solutions manual does it. So I'm going to do it a little differently. Right now, I'm going to build this integral. This becomes the integral. I know that the volume of E for this guy is going to equal the integral from 0 to 1, the integral from 0 to 1 minus x, and the integral from 0 to 1 minus x minus y, and then I just build out my dv. However, remember, I started with limits on z, so this is dz. These were limits on y, so this is dy. These were limits on x, so this was dx. Okay? I also know that E can be defined using this exact same D1 as the set of, those are getting uglier and uglier, aren't they? X, Y, Z, such that now, how can I set up a different integral? Well, in this one, my last integral that I did was from 0 to 1, and those limits were on X. Well, now I'm going to do those on Y. All right? I'm going to use this guy. So I'm going to go Y between 0 and 1. X is going to live between 0 and 1 minus y. And z is going to live between, again, what? 0 and 1 minus x minus y. Because all we did with these first two moves was establish that we were dealing with this D1 region down here. All right? And you can probably tell what happens. This is equal to the integral from 0 to 1. Those are limits on y. We got to pay attention to that. 0 to 1 minus y, and then from 0 to what? 1 minus x minus y. And then now instead of dz, dy, dx, I've got dz, dx, dy. All right? Right? And this guy is going to equal the volume of my enclosure. Now I'm going to walk you through, I'm not going to walk you through all 6 because you'll want to kill me, but I'm going to walk you through 2. I'll just kind of pick them at random. I'll pick, well, let's do this guy, and then let's do this guy, okay? So E is also equal to, now we got to be careful here because now my domain is in the YZ, so I'm going to put my little D2 up here, all right? Now think about this. I've got the set of all points, X, Y, Z, such that, which one did I say I do? I said this guy. So Z is going to live between 0 and 1. I should have done this with different ones. I apologize, guys. It would have been more fun with if the numbers were, if something was different than from 0 to 1, but it doesn't really matter. Okay, Z is between 0 and 1, right? I know that Y lives between 0 and 1 minus Z. Now, where does X live? Well, X now is being defined by this plane coming out away from the YZ plane. Well, X is equal to 1 minus X, 1 minus Y minus Z, right? I don't know what just happened there. I'm going to leave that alone now. X equals 1 minus Y minus Z. So now X lives between 0 and that guy, which is 1 minus Y minus Z, right? And so the integral becomes what? All you do is you move left to right. Integral of 0 to 1. Integral from 0 to 1 minus z. Integral from 0 to 1 minus y minus z. And then this is always, when I'm finding volumes of these enclosures, it's always just 1 dv. And my dv is defined by, and I work inside out. So this is dx. What was this? Dy and dz. Okay? You know what? I'm not even going to make you live through that last one. Hopefully you can do it. Now, these are very, very simple regions. Let me be clear. Should I do one more? Nah, you guys would hate me. But suffice it to say, we'd be making this guy D3. We would now define y equals 1 minus x minus z, right? And then I would have limits. Let's see, I would go 0 to 1, 0 to 1 minus x, and then 0 to 1 minus x minus z. So I would end up with, oops, this is my volume, by the way. I should have put volume here. I got equal signs flying everywhere. Volume of my enclosure. My last one, without having to write the whole E thing, my volume of my enclosure would be the integral from 0 to 1, integral from 0 to 1 minus x, and then my integral from 0 to 1 minus x minus z, and this would be dy. What do we got here? dz and dx. And that's how she works, okay? These are very simple. They can get really, really complicated, and we will do problems that will make you a little bit crazy. But at the end of the day, the ability to write 6, can you tell that there's going to be 1? It's going to be 2 for each one of these domains. So I've got 3 total domains, so I'm going to have 6 total integrals, 6 total possible ways that I can do this. Excuse me. This can get really confusing, but at the end of the day, the reason that we should at least be comfortable rewriting integrals in different ways is so that we can write them in the easiest way. Find the easiest way to write the integral when we go to find these volumes. Now, again, I don't want this video to be 9 hours long, and it could easily be an hour-long video, and I don't want that. So what I'm going to do is I'm going to cut it off here, and we're just going to talk and talk and talk about this in class. We got lots of time. It's truly not a very difficult section. It just gets a little confusing from time to time. So I'll see you in class. Thank you for your time and attention. And hey, that's triple integrals, man. And once we know how triple integrals work, it gets crazy. In the next sections, we're going to be talking about cylindrical and spherical coordinates, which are super fun. All right, I'll talk to you soon. See you in class tomorrow. Bye-bye.